video recording expert, Nima, standing in for Bob. So I'm so pleased to see a good turnout today. I know it was very last minute, apologies for that, but we just had a really great opportunity. Professor Lipson was in town for the York University Board of Governors meeting downtown, and we managed to convince him to take the train up to give his seminar before he has to fly back to New York. So thank you very much for arranging that. I'll just give a very brief introduction because I think Hod will talk a bit about his origin story in the talk, but Hod is a professor of engineering at Columbia University, and I believe the chair of the mechanical engineering department there. And he directs the Creative Machines Lab. And I think that's what we're going to hear about in the talk today. So a PhD from Technion, I believe. And actually just earlier this week, we were meeting with the president of Technion here at York and trying to create some synergies and some collaborative projects. So very famous institution in Israel. And I believe you were previously on faculty at Cornell University. Before coming to Columbia, did your postdocs, I think, at Brandeis and MIT, right? He's a very well-known researcher in a broad range of fields, has written a couple of very popular books on 3D printing and autonomous driving, and is particularly famous for his work on machines and creativity, and I guess evolutionary learning in that context. And so I won't say any more, but very pleased to have you
here. All right, thank you. Yeah. Thank you. It's a pleasure to be here today. And I actually, how many people here are graduate students? All right, or students. All right, great. So I went through a little bit of a, no, it's not going to be the usual talk where I just tell you some cool result that we got, but rather it's a little bit of a story of how we got to these results, and a little bit of serendipity involved. So a lot of research, as if you're starting your career, you might think that you can plan your research and you're going to get what you set out to get, but a lot of it is random. And this is a little bit of our story, my group, in this area of automating of AI and science. This is not a talk about deep learning, all right? This is not a deep learning talk. It's unusual, but we're going to use a different kind of AI, which is called evolutionary computation. I think these are the two AIs that remain standing, the evolution and the neural, and they kind of bring different things. But my background is robotics. I've always been interested in robotics, and if you're interested in robotics, you know that there's sort of robots today are better than human in almost any way you want to measure. They're faster, they're precise, they're very powerful, they work 24/7, but the main challenge with robots still is adaptation. Adapting to new situation. And the big question is, can you make robots that can be adaptive? So I started my academic career at Brandeis University. After finishing my PhD, I came to do a postdoc at MIT and at Brandeis. Brandeis University, that's in the shadow of MIT. And this is a Volin Center for Complex Systems. It's a math, computer science center. This is what it looks like on a good day. And over there, I started working with my advisor at the time, Jordan Pollack, on this kind of idea where we're going to breed robots. Instead of, is this the camera? I'm going to stay away from it. We're going to breed robots instead of trying to design them. So the idea is that we create a big physics simulator. We throw in lots of pieces of robots, bars, motors, joints, neurons as in neural networks, all these different components. We hook them together in random ways, and we take the ones that do better and co-breed them and replace the ones that do less well, and we breed robots for a particular purpose. Let's say for crawling across an infinite plane. That's a very simple goal. So that's easier said than done. Back then, this was 2000. The year was 2000. You couldn't just download a physics simulator. Today, you just download it, it's no problem. Back then, we had to write our own physics simulator from scratch. Then we ran it on the biggest, baddest computer we could find, which was the older people might remember Silicon Graphics. This is an Onyx 16 processor, blah, 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 state of the art, slower than your cell phone today, but it was the biggest machine. There was one of this on campus, and we got some time on it, 16 processors. We threw in all the components, we hit enter, and prayed for something to come out. Now, long story short, this is a chart that shows each dot here is a robot. This is the speed, and this is generation. And every click here is 50 generations, about a week of running on this 16 processor computer. So we run this thing for a long time, and here I was almost ready to unplug. You know, give up my academic career, go in the industry, do something useful. But then something happened. Suddenly, a bunch of neurons and bars and motors connected together into a pile of garbage that wasn't moving anywhere fast, but it was vibrating a tiny amount. And that tiny motion was infinitely better than the other piles of garbage that were not moving at all. So these vibrating piles of garbage took over, and next thing you know, things started moving forward, and it kept on moving forward and up and up. And after a while, I started getting these interesting robots flying across the infinite plane. Here are two successful ones. These are my two favorite. This one is my favorite because it kind of wiggles its tails. It looks almost like it's engineered. You'll notice they're symmetric. That was not part of the reward. It's just the fact that probably moving in a straight or in a fastest requires you to be symmetric. There's interesting insights there. But this is what it looked like. This one evolved at Brandeis. This one evolved at MIT. I would put these on every computer that I could find before I left home, come in the morning and see what I would find. But to take it up a notch, I also got a 3D printer. 3D printers back in 2000 were a new thing, and they were very expensive. A 3D printer cost $100,000. And I 3D printed a couple of these robots. Here they are crawling across the floor. Now today this isn't impressive, but back then it was a big deal. Today, or since then, we've been doing a lot of other experiments with soft robots that are much harder to simulate. This is an example of evolving soft robots. This is actually a homework assignment in one of my design automation classes. This is a parade of soft robots evolving in the same idea. The physics simulation is more advanced, evolutionary techniques are more advanced, but it's the same old idea of robots that are evolving. And we're also working on making materials to actually instantiate this. This is a electric actuator of a soft material that actually expands and contracts. So that's a little bit of fast forward a decade. But if I go back to my story, this was my biggest accomplishment, is making these kinds of robots. This one made it to the front page of New York Times. And this is really all you need to get an academic career, okay? You need to get on the front page of something. This is, the editor of New York Times told me that the only reason they put it there was because there was nothing else happening in the world that day at all. The world was completely silent. So they had no choice but to put it, but it was all about robots taking over the world. It's sensational and so forth, but that got me my faculty position at Cornell University, and the kind of rest is history. So this is Cornell University, upstate New York, not far from here. This is what it looks like on a good day also. It's usually covered with snow, but this is a good day. And there I joined the mechanical engineering department. And in the mechanical engineering department, I knew that I'm not going to get tenure making plastic robots. I need to really kick it up a notch and make something more complicated. So this is one of my first robots. This was a kind of 9-legged machine. It can jump up in the air. There's a paintball canister in the center. There's air pressure. It's a very powerful machine. And my goal was to make this machine gallop in the fields, like really do something amazing. And this was a time where control theory control something like this in any systematic way, and we'll see how far it goes. So I built this this cage. My students put this robot inside. We were tracking this ball from a camera at the top left there. We evolved controllers that would make the robot walk, reward the controllers that do better by cross-breeding them with other controllers. These are all neural networks, and we hope that eventually we'll get controllers that make the robot move forward. So actually, this audio that's not playing, that's my fault. But anyway, it's just a clickety-clack robot. This is a playback of some of these behaviors. But as you can see, I was not going to get tenure. These robots are not moving fast. They're not galloping in the fields. This is underwhelming, and it's not going to go anywhere. So, so we have a problem. This is already 3 years into my academic position. So to summarize, I showed you 2 projects already. The first one, we built robots. We evolved them in simulation. We then took the best one, built it in reality, and it worked. But it only worked because the robots were really, really simple and quasi-static. There was no dynamics involved. So it works, but we have this what's called the sim to real problem. And it only works when your robots are very simple. You can breed them in simulation and hope they work in reality. But it doesn't work for complex systems. The second project, we evolved everything on the real robot. So there's no sim to real challenge. But the problem here is that it's too slow. It just takes too long. Every trial takes a few minutes. There's only a couple hundred trials you can do overnight, not enough to learn. So we have this challenge where either it's too slow or you have a reality gap. What do you do? So I'm going to show you now the third project, which is an attempt to sort of skip that whole challenge. So remember, this is about 2005. This is about 20 years ago where we did this. We said, okay, let's start with a simulator where we're going to breed all these robots. We're going to get the best robot. We're going to build it in reality. But I'm putting simulator in quotes there, because the simulator is not going to be a good simulator. It's going to be a bad simulator that's not very accurate. It's a crappy simulator. Then we're going to try it in reality. It's not going to work, but we're going to collect a ton of data. And then we use that data to breed better simulators. In other words, we are now not just breeding robots, we are breeding simulators at the same time. We are co-breeding robots and simulators. And these 2 things are going to work together. Simulators are going to get better at simulating robots. Robots are going to be better at walking inside the best simulators. And hopefully, and they're all going to be grounded by real data that you try once in a while. So we try this, and this kind of thing is what we call coevolution, or co-adaptation, or adversarial learning. There's different names for these right now, but this idea is that you don't have one thing learning, which is the classic machine learning approach. You have 2 things co-adapting at the same time. Now I would say this is very common. Almost all accomplishments in AI today, from Sora to video generation from text and text, they always involve multiple AIs training each other. Back then it was a new idea. And I urge you to always think about machine learning in groups, not ever as a one thing learning towards a static goal, but always think about how you can pitch multiple AIs against each other. It always works better that way. So we tried it on this third robot. So this is a third robot I'm going to show. This robot is interesting. This robot is blind. It does not know what it looks like. It doesn't see the world. It doesn't know if it's a spider, a robotic arm, a worm. It doesn't know what it looks like. All that it knows is that it has 8 motors, 2 on one at the hip, 1 at the knee of the 4 legs. But it doesn't know even that it has 4 legs. It just knows it has 8 motors, and it has 2 sensors, 2 tilt sensors that tell us it's tilted left and right, forward and backwards. And this robot needs to learn how to walk. But again, it doesn't know what it looks like, what its shape is, what its morphology. So to understand what that means, imagine yourself for a moment sitting in a black box where you have no windows. You're in a black box and you have 8 knobs. And as you turn the 8 knobs, you can feel the box tilting forward and backwards, left and right, and you need to make this robot move, this box move forward. How do you do it? You can do trial and error, or you can do something more complicated. So this is what this robot feels. What it feels like, maybe it's not unlike what the brain of a newborn child feels, where it has all these muscles and actuators and it has to do stuff and it doesn't know what it is when it's in it. So we start off by the robot making random motions, and then it starts building a model of itself. And it starts building hypotheses of what it might be. Maybe it's a snake, maybe it's a spider, lots of random assemblies. And it's looking for things that match up the little bit of data that it has, that it experienced. And this is the top left image of a bunch of things. And now, bunch of candidate hypotheses. And I hope you'll in a moment, you'll get a feeling for a scientist emerge out of this. And then, and this is the key step, it goes to this green box where it looks at what motor commands should it execute to cause disagreement between predictions of these models. All right, this is a key thing. This is a little bit like a scientist designing an experiment. And what's the best experiment to design is one that causes disagreement between predictions of 2 competing theories. Because then the result from the experiments will refute at least one of the theories.
Yes. Does it have concepts of snake or spider in its memory?
No, just topology that can connect sort of Lego bits to each other. So it does that, collects more data, refutes some of the models, tries it again, and after it does this a few cycles, this takes a lot of compute of relatively few physical trials, so it's grounded but doesn't take a lot of effort. And after it does it enough times where it cannot make the models disagree with reality anymore, at that point it uses one of these models, that they're all identical, to learn how to walk. And what makes the robot walk in simulation will make it walk in reality as well, because reality matches the simulation. So that's the idea. So we tried it out. This is one of the first time we ran this robot. You can see it here on the ground, and it kind of it just moves around and tries to model itself randomly, and it's unplugged itself and died. And this is kind of a little bit of a lesson. You don't want to go too wild and jump off a cliff to see if you can fly, but this is what this robot is doing. But after we tamed it a little bit, it actually worked. This is one of the successful runs. It took about 4 days. We're sort of peeking into, we're playing back all the models that the robot is creating. This is about 2 days into the process. It's figuring out that it has 4 legs. It doesn't quite know where they're connected and how. This is about 4 days into the process, and it created a pretty accurate self-model. That model is good enough that it can learn how to walk in its imagination, and here it is walking in its imagination, if you like, in the simulation it built for itself, and here it is walking in reality for the first time. So this is kind of, we were hoping to get an evil spidery walk, but instead we get this lame way of moving forward, but it's still interesting, good enough for a publication. But again, when you look at this, you have to remember it did not do trials of walking before this. All it did is a random perturbation, thought about it, and then walked away. To try something with it, we did something very cruel. We plucked off a leg, and we watched what happened. We plucked off a leg, and the robot, within about a day, its self-model also loses a leg. And you can see here the leg, the pink leg, becomes very short. And then it switches to, it basically evolves a new way of moving forward that uses this short leg. And now I know it's very sad, but we did put the leg back. The robot is happily retired. But you can see that the robot doesn't, it's not that there was a sensor that said leg came off, switch to plan B. If the leg came off, therefore the dynamic changed, therefore the self-model changed, therefore the behavior changed. So we're after adaptation, and the idea is that self-modeling, this ability to adapt, is really, it's all about resilience Later on, so there's a lot of interesting questions around this in how machines model themselves. And one of my pet projects is sort of thinking about self-awareness and how machines evaluate themselves and so forth. But here's some statistics. The origin and the red dots are where, the origin is where the robot starts. The red dots are what a random controller does to a robot, where it ends up. The black dots are where the robot believes it's going to reach using its self-model. And the blue dots are where it actually goes in reality. So you can see that like anything else in academia, this robot has an inflated self-image. It believes it can go twice as far as it really can. Nevertheless, it's interesting, even though the self-model is inaccurate by a factor of 2, it still allows it to make the right kind of decisions. And this is interesting that evolution doesn't necessarily care about being accurate. It's all about whether the model allows it to make the right kind of decision. And there's interesting papers about modeling for control is different than just modeling. If you're only interested in controlling something, sometimes the requirements of how accurate your model needs to be can be relaxed. So it's interesting to see how that happens. Since then, we've done a lot of work. This is 6 years ago, it seems like yesterday. This is a deep learning model. You can see in the background how the robot, what it looks like. And this is, the shadow is the self-model created now. This is with deep learning, much more sophisticated, much fewer assumptions. This robot doesn't know any physics whatsoever, but the self-model allows it to plan, and we can even break the robot, and it just moves about a little bit and adapts its self-model. And this is the latest thing. Actually, there's another paper that just came out a few months ago, but here this is a statistical model. That cloud is how the robot sees itself and how it reconstructs itself simply by looking at the mirror and seeing how it moves and so forth. So we're working a lot on this idea of robots modeling themselves with less and less information. And I think it has to do a little bit with how we humans see ourselves. So this is sort of begins to touch in psychology. If you close your eyes and you imagine where you are in space, we have a notion of sort of physical self-awareness of where we are and where we're not. And robots are beginning to learn that kind of notion of self-awareness. And it has a finite accuracy, but we use it as we move around, as we exist, and so forth. So a lot of research in how robots model themselves, how robots model other robots, by looking at other robots, all this robot sociology, if you like. I think it's going to be a big field. It's unfolding, but it's not what I want to talk about. That's a whole different field. We're doing a lot of research there, but I want to tell you back to the story, what happened after we made that robot, that 4-legged robot that was modeling itself. So we published it, it got a lot of press, but then a new student came to the lab and said, look, all you're doing here is you're modeling, you're doing active learning on a black box. You have a dynamical system, you can perturb the inputs, observe the outputs, perturb the inputs in a clever way, observe more outputs, and you want to know what's in the black box, and the black box is a hidden dynamical system. So let's take the same process, but instead of a robot, put some arbitrary, complicated dynamical system, maybe a chemical system or whatever. Instead of making models out of pieces of robots, let's make models out of pieces of math. Differential equations, plus, minus, divide, multiply, algebraic operators. Instead of perturbing the motor commands, let's perturb the initial conditions of the experiments and see if we can create models of hidden systems. And we use the same idea again. Now, where does the data come from? From a disgruntled scientist collecting data for the AI that's doing the thinking. This is a little bit of a turn of the tables. We humans thought that we're going to come up with the hypotheses. The AI is coming up with the hypotheses, but we're good at collecting data. Could be another robot, could be a big database of experiments. So either whatever you want to do, it could be different things, but this is the cycle. So we tried it on a bunch of different things. So this is actually, I don't know if anybody here has been to Cornell. Cornell University is on a cliff, and you have to cross a footbridge to get in. This is the footbridge. It's very easy to defend. in case you ever have any plans. Very easy to defend Cornell. So this is a footbridge I would cross every day. And as you cross this footbridge, it was very shaky. And I was always wondering, is there a way to tell if one of these slats are a bit weaker than they need to be? So we created this software that vibrates the bridge in different random locations, creates models of how weak they are, and then figures out how to vibrate the bridge again in a way that causes the models to disagree in their predictions. The same idea of models and data against themselves. And we could show that we can find the weak link a lot faster and more accurately than traditional civil engineering approaches. So this idea of co-optimization and interrogation work really nicely. This is with Wilkins. This was about, again, 15 years ago. I moved to Columbia. Wilkins moved to Duke, but the bridge remains. So lots of attempts to do this in different areas. Another student came along and applied this to electrical systems. It's an analog circuit in a black box, perturbs the non-linear analog circuit, perturbs the analog circuit in different ways, and can figure out what's in the analog circuit. So from a black box. So same idea. You just change the language. You turn the perturbation, the two systems interrogate each other. But that's not what I want to talk about. I want to talk about what happened next after we started with the math building blocks. So the math building blocks is related to this idea called symbolic regression. So I presume you all know what linear regression is and nonlinear regression is. And this is when you have data and you have a model and you fit the coefficients of the model so that it fits the data, right? That's regression. Symbolic regression is we don't even have a model, right? So for example, if I ask you, what is the equation that fits this data? Anybody guess?
Mixture.
What is it?
Mixture.
No, well, something specific. Give me a math, not a rhetoric question.
Gabor function.
Too high. Give me something simple. Anybody guess? Okay, you're all timid. You're all skirting around it. Okay, this is a sine times exponential.
Okay.
All right? Now, if you were doing this in your head, you were already kind of doing simple. You know about building blocks, exponents. You know about trigonometric functions. You have these building blocks. You don't know the coefficient, but you try to put them together to qualitatively get this kind of shape. All right? So that's the function, and it can get all harder. Like, what's this one? This is a lot harder, and so on. So if you take this, so the idea is with symbolic regression is that you breed equations, just like you're breeding robots. When you put all these math pieces together and you start, this is a tree that says x here, x minus 3 times sine of x plus minus 7, right? So this is an expression. You can crossbreed these expressions, do all kinds of things. You start with your data, you measure the error, you breed equations that have reduced error, and you finally get your model. All right? So that's the idea. This is called symbolic regression. It's been around since the 90s, all right? So for 100 years, okay? Not a new idea. But there's only one problem with this idea, and that is that it doesn't work. Why doesn't it work? The two reasons most machine learning algorithms don't work. It takes a lot of compute, and it overfits the data. All right, so we're stuck with these two problems. So what do we do? So what we did is we went back and we basically brought in this idea of two competing things that are co-evolving at the same time. We are going to keep evolving models to fit the data. But here's the trick. We don't fit them to the entire data set. We only fit it to a few points in red here. You see? These are selected points from the green data set. Which points do we choose? Well, these points are co-evolving to defeat the models, to create the most disagreement between the models, right? So the models are fitting the red dots, but the red dots are jumping around to create disagreement between the models, right? So it's like models are trying to explain the data, but the data is jumping around to break the models, all right? It's like student-professor type of relationship, predator-prey. I don't know what analogy is, but they're working together. And this is one of the first runs. We ran it, loading the data set here. Here's the original data set. You see the red dots jumping around. And lo and behold, very quickly, it says this is a sine times an exponential. Very quickly, it finds a solution. So it worked so well and so fast. I thought maybe it's reading the file name. So we changed the file name and it still works. So it's kind of a cool thing. And in fact, we ran it multiple times. We could see that when you co-evolve the data, it works, it finds a solution faster and more accurately than when you train on the entire data set. And this is very, very strange because you would think that throwing more data at a problem is better. But what this says is no, you throw less data, but the data has to be co-evolved to defeat the models. It's a very important sort of concept, but once you do it that way, the data targets weaknesses in the models and the whole thing picks up. And this is kind of the key of adversarial learning today, is that relationship between two things that work. But you can see here the co-evolved data set finds a solution more accurately and sooner, and it defeats random selection of data, subsampling the data, all kinds of other baselines. And importantly, the solutions are simpler. They're just as accurate, but they are simpler. So co-evolved data set gives you simpler solutions for the same accuracy. So it also avoids some of the overfitting solutions. So it sounds like the magic solution. We found it. So of course, first thing we did is we tried it on the stock market. Now, I'm still here, so obviously that didn't work. But we did try it. And it turns out there's more to the stock market than fitting curves. It's about what data you have access to, a long story. So we said, okay, let's try something else. Let's try to let's find an equation for the prime numbers. Let's go for gold. We put in the prime numbers and we found some approximations that are well known, but nothing groundbreaking. So seeing we're not going to be rich or famous, we wrote a paper about this and just saw what happened. So we published a paper, and then I got this email from somebody in CERN, the particle accelerator in Switzerland, and he said, we have the perfect problem for you. We have a gap in the binding energy of atomic nuclei. I'm not sure what that even means, but he has a spreadsheet with data. He says, find the equation that explains this gap. We plug in the data, we hit enter, we wait, we get this equation, good for 3 digits. I quickly emailed the guy at CERN. I said, we got the equation for you. What happens next? And he said, he emailed me immediately and he said, we already know about this formula. It's called the Weizsäcker's formula, and our formula is good to 4 digits. So he was disappointed, but I was actually very encouraged. Wait a minute, we can find named formulas for things that, we just need to find the right kind of data set and we'll be rich and famous. Okay, we just need to find the right data set. But we're going to take it up a notch. And instead of just fitting curves to data, let's fit curves to the derivatives of time series data. And if we can do that, we're going to get differential equation models, which are much more powerful than just curve fitting. So we take time series data, we compute the derivatives, easier said than done, and then we fit the data to it and we see what happens. So the first experiment we did was we took the 7 differential equations of the glycolysis cycle of the cell. I also don't know what that means, but it looks pretty complicated to me. Take these cells, produce data, sprinkle some noise, run it through the algorithm, and lo and behold, bam, it finds the 7 differential equations simply by looking at the data, and it's only given plus, minus, divide, multiply, open brackets, close brackets. Bam! It only got this thing, which is wrong, but very small. So we have this tool that can find pretty complex differential equations simply by looking at noisy data. What do we do with this? So one of the things we applied it to is, so we do a lot of work also on regular robots and flying robots and walking robots. So this is one of our robots. It's a flying mosquito type thing. It's very small and it flaps its wings and generates lift. So this is called aeroelastic lift. It's a very complex phenomena. People spend careers trying to model aeroelastic lift. We said, hey, let's collect some data, plug it into our system, see what happens. So we plug it in. This actually, we never published this. Charlie was stolen by MIT, and he went to do a PhD there and abandoned. But the project worked beautifully. He took this, he collected the data, and he got some interesting models. Now, I don't want to show you the models per se, because they're not interesting. I want to compare them to state-of-the-art models, derived by human experts. And I'm going to compare them on two axes, which are arguably relevant to all of science, and that's accuracy and simplicity. And when we scientists come up with theories, we have a choice. We can come up with theories that are simple but not very accurate. F equal ma, pretty good, but it's not perfect. You can have models that are accurate but complex, and sometimes we need them. This is where you get the Nobel Prize, E equal mc squared, whatever. And unfortunately, most of us end up here, right? But this is the landscape of scientific discovery. There's a lot of space here, many PhDs in between in this space. So where did the models for this flapping aeroelastic lift end up? So we surveyed the literature. Here are all kinds of models. We had a very rigorous measure of the accuracy and complexity for the phenomena that we were measuring, the fine-tuned, adapted. These are the models generated by our software. And you can see they are simpler and more accurate than the models created by scientists. So according to Occam's razor, they must be closer to the truth than all of the Ishdati or somebody's career. And there it is. These are polynomial fits as well. With this tool in hand, a lot of interesting students started pouring into the lab. This is one student, I remember he came in, he says, I want to model road tire interaction. And I thought, oh, that's so noble, he wants to, for car safety. And he said, no, for video games. Okay, so he said for video games, and sure enough, he got models, the red dot, that are more accurate and simpler than state-of-the-art road tire interaction models, and so forth. So lots of these examples, and I, at that point, started giving a lot of colloquiums around the planet, telling people, hey, I have this hammer, I'm looking for nails. I can make models out of data. You give me the data, and I'll give you the model. And we can work together. Now, of course, people don't want to share the data. This is kind of the classic problem of machine learning people getting the data. The data is always the asset. Now, one guy, Girl Sewell, came to me after one talk, and he said, I have the perfect data set for you. I'm measuring Bacillus subtilis, which also I don't know what these are, but they're important to some people. And he's measuring markers in these cells as they go up and down over time. And he says, I have 60 cells. I measure these markers over time for every cell separately, which was different at the time where people just do VATs of a billion cells. So I got the dynamics. Maybe you can look at this and tell me what is the model that explains this dynamic across all cells. Maybe different coefficients for different cells, but the same dynamic. And he gave me a spreadsheet with 60 cells. A very precious little data set that took him 10 years to collect. And he said, see what you can find. So we plug in this thing, we run our dynamical system, we compute the derivatives, fit the curves, do the whole thing, we hit enter, we wait for a week, and we get these answers at the top. Two differential equations that kind of explain the data, but not really. Kind of. So I send it to Gural by email, and he emails me back and he says, this is total garbage. It doesn't have to do anything with biology. It's even second order. There's no second order in biology. This is total garbage. It's nothing to do with reality. This is a bit harsh, but we were depressed for a week, and we knew we were doing something wrong. We are missing something important here. And we realized first of all, we put sine and cosine in it, but there's no sine and cosine in biology. So we're using the wrong building blocks. But we're also missing some building blocks. It's important to biology when we didn't give the toolbox. And then we realized we were missing time delays. So in biology, unlike physics, there are time delays. There's diffusion, things don't happen exactly at the right time. We put in time delays, we hit enter, and bam, you get these two beautiful equations that explain the entire data set. I emailed Gural these two equations, and he said, we have a problem. Here's the state of the art, and your equations are simpler and more accurate. And happen to be his state of the art equations. The problem is that we have no clue what they mean. It's a little bit like copying homework for someone. You have the answer, it works, it fits, but you can't explain how you got it. And this is where we were stuck. So we never published it because nobody was willing to publish it, but it fits the entire data set perfectly, including new cell lines that were not seen before. It's just there. Couldn't publish it. That paper is still sitting somewhere. So that brings me to the last piece of the puzzle, which is searching for meaning. Like, how do we know what the equations mean? So this thing evolves equations. How do we know what it means? And it's not this kind of meaning, but it's sort of, how do we actually know the mathematical meaning of these equations? And this is very different than your classic machine learning, which is all about predictions, right? There's this classic thing, I know this is a classic exercise now. People, if you look at supermarket data, you find out that people that buy diapers on Thursdays also buy beer. That's true. And if you're running a supermarket, you don't care why. You just put the beers next to the diapers and you sell more. But we want to know why, what is driving things, what's behind the scenes. So to do that, we decided we're going to look for invariance. And this is the key thing. We're going to look for what is not changing about the data. This is kind of an insight. We're going to look for invariance. Because this notion that all of science is about looking for invariance. Another theorem around this, looking for invariance. So I want to do a little exercise here. This is a pendulum, and let's say we're measuring angle and angular velocity of the pendulum. Angle and angular velocity, this is physics 101. What is not changing about the angle and angular velocity over time? Is there some constant? Is the ratio constant? Anybody guess what is not changing about angle and angular velocity over time?
The maximum.
The maximum is not changing, but what is, if I look at every instance, what's the constant?
The energy of the system.
Energy, that's right. Who said that? That's right. The energy is good. Usually people don't get this. Or in other words, the Hamiltonian is the energy of the system. The Hamiltonian is the constant. And physicists will tell you, if you can find the Hamiltonian of a system, you know everything there is to know about it. So exactly. So we want to know what is not changing about these two variables, or whatever variables we can measure. So we took, this is a double pendulum. We measured 4 variables on a double pendulum, the angle and angular velocity of the 2 arms, and we asked, what is not changing about these 4 variables? Now, what combination is not changing? Now, this is very easy to do in evolutionary algorithms. You just reward the function for finding some equation that reduces the variance across the entire data set. So we put it in, we hit enter, and we wait. We waited for about a week, and then we finally got the answer. The answer came out, and it was a constant. A constant is not changing across the data set. Problem solved. This is a function that is constant, and it's invariant. It's great. The only problem is that it doesn't use the 4 variables. So another student came along and says, we're going to penalize the AI and we'll force it to find an invariant function that also uses the variable. We put it in, we put the penalty, we hit enter, and it comes back with this. This uses the variable, but it's not what we want. Another student comes along and says, I can take these out using symbolic analysis, blah, blah, blah. It comes back, and it comes back with this, which is almost invariant, but you can't remove the. It's like arguing with a teenager. it comes back with all kinds of things. It's not what you want, but it's what you asked for. This is what AI looks like. So eventually I did what most professors do in this situation. I gave it as homework. I actually did. I said, here's a homework assignment. Here are 3 data sets, find the invariant. Now, to be fair, I gave it as a bonus homework, okay? So it says, if you can find how to formulate the fitness function so it actually finds the invariant, you get some extra points. And one student, Michael Schmidt, came back and said, oh, it's easy. Here's the function, and if you put it in there, back here are the, here they are. So, and he's, by the way, CTO of Data Robot today, but he found the invariance at the time. So how did he do it? Well, the idea was very simple. He said, look, if you have the derivatives, you can compute the x dy, dx of if you have x and y variables as function of time. If you have a candidate invariant f, you can compute symbolically the f dx. You can symbolically compute the f dy. The ratio between them should be dx dy. It should match what you get from the data, and the system cannot cheat. It has to actually be a real invariant f to match this thing. And sure enough, he tracked, first was a pendulum, an oscillator, and collected data, and this is what it looks like. And after a while, it came back with Hamiltonian and the Lagrangian of an oscillator. Then took a pendulum, and he got the Hamiltonian Lagrangian of a pendulum down there. Takes a few minutes. This is a double oscillator. This is already 3 springs, 2 masses. Here's the data. What's not changing about these 2 curves? Well, this is not changing. That's the Hamiltonian of a double oscillator. This is already, takes a little bit of a graduate physics knowledge to do something like that. I couldn't do that without being prepped. Then we went back to that double pendulum, a famous double pendulum. This is Steve Strogatz at Cornell with this double pendulum. What is not changing about it? Well, first of all, we track it with an LED in the dark, which it makes these beautiful art pieces. What is not changing about it? So this is what the data actually looks like. Here are the 4 variables. This is a snapshot of these co-evolved models behind the scenes, how it's evolving. This takes about a day of doing this kind of thing, and eventually it comes back with the Hamiltonian of a double pendulum, conservation of energy, all kinds of interesting things about Newtonian mechanics simply by looking at these 4 variables. And by the way, we also found the Hamiltonian of that cell that explained these 2 equations that we found for the cell. We still didn't publish it because Mike already graduated, but we found the invariant there. So I showed you 2 examples. One, finding Hamiltonians of mechanical systems. The second one for finding biological systems. But these are all symbolic scientific models. These are not deep learning models that are opaque. These are models that you can read, you can write, you can even put them in a paper and claim that you thought about them themselves. And I think a lot of people do this now. They use the software, they come up with models and they say, I thought about it hard and this is what I came up with. And there's no way to prove that the software did it because it's symbolic. Since then, people have done all kinds of PhDs in this area. Stochastic modeling, where you have noise elements. This is reaction modeling for modeling diffusion and chemical reactions. Find out whether the reaction models that explain data. Hybrid systems, each one of these things is a PhD, but it's an idea of how you look at raw data and you create symbolic models that people understand. But I want to end with something that kind of always bothered me with all these projects. In all these projects I showed you, we're all about, the human measures a couple of variables and the AI creates the model. But how did the human know to measure these variables in the first place? Like, how did I know to measure angle and angular velocity to begin with? And I'm just looking at a pendulum. People have stared at pendulums for probably thousands of years. they never thought of measuring angular velocity, right? So how do we even come up with the concept of measuring a variable? And arguably, until you measure the right variables, you can't come up with a model. The variables precede modeling. Most of us scientists, we engage in modeling assuming we already know the variables. So the question is, step one is coming up with what to measure, and step two is giving this data, finding the model. We automated this. Can you automate this step where you just look at something and you find out what the variables are? This is kind of the biggest challenge, and it's a much harder challenge than doing this. So to address this, this is where deep learning does come in. We created a system that starts by just looking at a video of a physical system. This is a real double pendulum. This is just captures the video. And the first thing it does, we just train a deep learning system to predict the future of that video. And the assumption is if the AI can predict the future frames of this double pendulum, you know, in this case, half a second in advance, it must know something about the dynamics in order to do it. At that point, we can squeeze that autoencoder in the center, and it actually works even better with a transformer. We can squeeze it to find the state variables. Now, how far can you squeeze it? That's the question. This video, you take 2 frames, predict 2 frames. You have maybe 50 or 100,000 variables. In this case, we know that the answer is 4, because a double pendulum can be described with 4 variables. But there are certain mathematical techniques that will tell you how much you can squeeze it. There's a lot of details in how you squeeze 100,000 variables into 4. You can't do it all at once, but let's say eventually you can do it. And it tells you for the double pendulum, in this case we got 4.7. You can squeeze that entire video into 4.7 variables per frame. And we know that a double pendulum can be described with 4 variables. Probably the 0.7 has to do with probably dithering resolution or something like that. Here it is. You give it, you know, how many variables are needed to describe this flame here? The answer is, first of all, you make the prediction, and then the answer is 24. And it's pretty rigorous. In fact, we ran it on a bunch of dynamical systems. This is a flexible double pendulum, elastic double pendulum, for which we know these are systems we know the answer. We know the answer. This one we don't know the ground truth, the lava lamp, and all of them. So when we know the ground truth, it matches pretty well. It can tell us how many variables. And we don't know, but still it compresses them very well. So we get the variables for these dynamical systems from observation, and from there, once we have these models, these variables, we can start using the traditional control theory, all the analytical methods, because we actually have the variables. This is work by Boyuan Chen, who's now a professor at Duke, who did some of this work and moved on. So you can see the variables here. Now, the last thing I want to say about this, that the variables that the AI finds are not unique. So the 4 variables we humans choose to describe a double pendulum, angle and angular velocity, are not unique. You could choose other 4 variables like coordinates or energy or all kinds of other things. So what kind of variables does the AI choose? So in general, when we plot the variables, we get all kinds of random things, but we found out that by smoothing the variables, we get the best things. So I want to emphasize this because I think if you look at historically, I think the great scientists historically, their greatness is not that they came up with the models, but that they came up with the variables. That's the real contribution of scientists. If you look at Newton, Newton came up with a concept of acceleration. It's hard to imagine, but before Newton, people didn't have a concept of acceleration. They knew that things can go faster or slower, but to quantify it as a number was inconceivable. He came up with a concept of acceleration, and frankly, after you come up with a concept of acceleration, this is pretty easy. Not really, but you know, it's a linear equation. coming up with a variable is the thing. And I think the fact that the AI can begin to do it is the key thing. And here's when we add smoothness, it begins to find variables that we recognize when we know the answer, and variables that we don't recognize when we don't know it. And I think this is going to be the future as we feed in more and more data into this system. New York Times still wrote about this work. He said theoretical physicists are not yet obsolete, but scientists have taken steps towards replacing themselves. I'm afraid that's kind of true. We are obsessed with taking ourselves out of the loop in trying to model these things, but we'll see how far we can push it. Thank you. Happy to take any questions.
That was great.
Two-part question. Why can't you publish the equation that solves the biology data? As an outsider, that's confusing.
It's just was rejected. So after 3 times, we can't give up. We can't just say, here's an equation, but we don't know how we got it.
You can't say that it's AI?
Yeah, but well, maybe today, maybe you could do it, but back 10 years ago, that was a faux pas.
That makes sense. I think you probably could say. I was wondering also, are you collaborating yet with the Artificial Science Lab at Max Planck Institute?
No, I don't think so.
They're doing similar stuff.
Yeah, okay, and so we actually, no, I have to look into what they're doing. Yeah, good question, thank you. Well, so where Chase to?
Max Planck?
Oh, next Planck. Okay, I have to look at it. Could be. At this point, there's a lot of groups that are, so I think, automation of scientific discovery is actually one of the frontiers where it's sort of either if you can't beat them, join them. So if AI is moving so quickly, let's just, ride this wave and try to accelerate scientific discovery. So there's more and more of this stuff. Yeah.
Well, I have a question.
Yeah.
I really enjoyed your talk.
Thank you.
Super interesting. So a little more detailed question. So when I guess earlier, you were talking in your robotics work, you were talking about selecting small models sort of randomly and looking at pieces of data, right? That was a key part. You don't overfit, right? So with problem overfitting, often we use cross-validation, right? So you use held up data.
Yeah.
And sort of these, in limit, you only hold up one data point, right? That way you have maximum training data. But you don't do that. You're using smaller partitions. So and one of the reasons for that is that the data are correlated. So, if you only hold up one data point, you actually in your training have a data point that's very close to that, so you're cheating, right? So there's ways of addressing that to estimate the true dimensionality of the data set, right? But then the second factor is you're trying to solve this non-convex problem, right? And so you want that randomness as well, right? So I guess long-winded, but the question is, isn't there kind of a black art there to decide what should the size of my partition be?
There is absolutely a black art in deciding. So actually, in the first paper we published this, we scanned. We said, okay, let's use 4 points, 8 points, 16 points, which we did it for different problems, and we tried to find out if there's any kind of relationship between how many points you need, and it's obviously related to the complexity of the problem. But we couldn't find a clear relationship. But you're absolutely right. There's a relation. It's not a fixed number. There's a relation. It could even change with time. It could be that in the beginning you need fewer points, and later on when you're optimizing the fine details, you need more.
Right.
It could be. So it's,
right.
Yeah. And I wish there was a theory.
Yeah.
That could guide that. Yeah. Yeah.
So just on the last part.
Super loud.
Thank you. The last part that you talked about, in terms of the new variables discovered by the networks. So my assumption, and please correct me if I'm wrong, is that many of these are not human interpreted. We don't really understand
Correct.
what they mean. Do you think there is, and this is sort of getting into the controversial topic of explainability,
Right. This is a terrific question. It goes to the philosophy of science. And why are we doing this in the first place? And I think if you're doing it to control something or to optimize, then you don't care. Then it's just variables. As long as they're predictive, you use them and good, and that's all good and well. But we derive some satisfaction from understanding. I do think that it could be that there's a small window of things we can understand as humans, and some things are too complex, and it's like explaining Shakespeare to a dog. Okay, there's just no way we can understand it. It doesn't matter how beautiful the AI is making it, we just won't get it. But I think we can extend the window of our human understanding a little bit using these tools. So I think that it's worth it. We're not at the end of the window. I think there's another couple decades and phenomena where we can use these tools to extend our visibility. But will we explain everything using techniques? No. I think there's something that's too complicated for this. It's a great question. Yeah.
If I had a problem that I wanted to apply these techniques to, how hard would it be? Is there any sort of open source software that I could download? I would have to implement everything from scratch based on research data?
Yeah. So there's not been a sad story here. Yes, there was an open source software. It was acquired by a company, and then they buried it because it competed with their own thing. So now there isn't, but there's other people's software. So if you look up for symbolic regression software, there's quite a few packages out there. I don't know if they use coevolution, but this is about, this came out in 2010, the first time. So it's been 15 years since. So I bet there is better and newer things. So just search for symbolic regression. And if you can't find anything, email me and I'll create something, because it's not that hard. The principle of this is it's really not that complicated. It's a very simple, it takes a lot of compute power, but the algorithm is fairly straightforward.
Yeah. For a follow-up question, today we use it to using deep learning techniques that require a lot of computing power in the form of GPUs, compared to what's the norm today. How expensive in terms of computing power are these techniques?
They're very expensive. So this will, so evolution uses a lot more computing power than deep learning, because it's a non-convex optimization. It doesn't follow a gradient, and the space is just as large. So we will waste whatever computing power you have. All right. So if computers are more powerful, it just means we'll solve harder problems. We'll still waste every last GPU that you can provide. And that seems to be the theme, right, in AI. The more computing power, the harder the problem that you can solve.
So yeah, on the creativity part, you showed some amazing examples of what I guess we'd call applied math, where you have some data and you want to. So Jeff Hinton gave a keynote a couple weeks ago at a innovation conference in Toronto, and one of the things he predicted was that the field of pure math will be one of the next things to fall, because in his words, it's a closed system and it's very accessible to AI methods for that reason, partly. And I just wondered if you thought about that at all, and because we think of math often as kind of a bastion of human creativity,
Right.
and sort of a pinnacle. Do you have you thought about that?
No, I haven't thought about it, but actually it makes sense to me that things we humans think are hard are actually very easy for AI, and the other way around. It's more of X paradox and things like that. I was just giving a presentation to your board at the university, and I was trying to make that point, that some fields that we think are very noble are actually easy, and they're going to fall. So interestingly, for example, so analytical things tend to be sort of easier for AI. Chess is very easy to AI. Tying your shoe with shoelaces is like a nightmare for a robot. That's like a multiple PhDs, all right? But playing chess is nothing, right? And so if you can tie your shoes, you're a genius. So I know it doesn't answer your question, but yeah, anything, we have this saying in our lab, if your hands are dirty, your job is safe. So if you're experimental and your hands are dirty, you probably your field is going to last a little bit longer. So make sure you're building something. Yeah.
I have a question. For things like image scaling, image processing, denoising, or interpolating frames in video games, people have come up with a lot of algorithms in the past that were simple but not that good. There's the big AI thing that's now taking over, but a lot of it, people have used horrible methods for measuring the results, like PSNR, which is endlessly shown to be visually horrible but still used because it's cheap. Or people develop these huge models of what human vision is and what humans like, and they generally are cumbersome and don't work. So I'm trying to think for something like this, for those kinds of applications, where you can try things, but they really have to be, to a large degree, finally evaluated by humans. And a good example is that picture could be perfect, but 3 pixels are flickering. Most models don't pick that up. Humans, you go right to the ugly pixels. Is there some way in this kind of adversarial work to somehow incorporate human feedback? Do you see that?
That's a good question. It's a great idea. I haven't thought about it too much. We did some work on interactive coevolution, where the human is one part of that adversarial relationship. We did it for co-evolving sort of art. I want to say art for design, where the human looks at things they like, and the AI is trying to figure out what they like and do more of it. So it's a little bit subjective, maybe relate to what you're saying. But I have to think about more about this.
Yeah, because I see what happens is you bring in the people building the algorithms to make these beautiful pictures. You bring in 50 people to evaluate them, they write terrible things.
Yeah.
But there's no, it just goes back to the developers.
Yeah.
Please fix the terrible things. There's no.
Yeah. So it sounds like a good, especially if you can automate it in some way. For example, if the image is bad and the eyeballs of the human go to then you can sort of almost automate some of that.
Okay.
So it's an interesting idea. All right.
More questions?
Thank you very
All right,
much.
well, thank you again. It's really amazing.
Thank you.
Okay, I want to welcome everybody to the CAIS Talks seminar. And welcome to our guest